I'm Nick.
I'm Kayla. This is OPTI 380A Lab 11 Detectors, and our TA is Susie. I have the photodiode detector under this with the green LED, and we can see the output on the oscilloscope, and on the top that's just the photodiode, and as you can see it has like a signal to noise ratio of 1. It's basically all just noise. And then the photodiode multiplier multiplies that signal, so it's a very readable cosine. The signal to noise ratio of the photodiode multiplier tube we found by taking the cursors and finding the peak to peak and then the difference for the noise, and it got an SNR of around 3.67. Here we have the photodiode directly connected to the oscilloscope. We have a peak to peak voltage of 432 millivolts, a fall time of 33 microseconds, and a rise time of around 3 milliseconds.
Here we have the readout on the oscilloscope when we added the resistor to the photodiode experiment. You can see the fall time of 83 microseconds, a rise time of 310 microseconds, and a peak-to-peak voltage of 3.08.
Using the peak-to-peak voltage value and the internal impedance of the oscilloscope, we calculated a maximum peak current of 4.32 microamps. This is the peak-to-peak and rise time for the photoconductor. We have a peak-to-peak voltage of 92 volts and a rise time of around 30 milliseconds. As you can see, this takes much longer than the other two setups.
Here we have the setup for the pyroelectric detector with the chopper. We read out a frequency of the chopper here, and the soldering iron is a source of heat, and we can read out the peak voltage values here.
So this is our graph of the peak-to-peak voltage versus frequency. As you can see, as frequency increased, voltage decreased.
So here we have the second setup for the pyroelectric detector section. We have an IR camera over there with the soldering iron now here in front of a mirror so that we can get an object and an image in the readout on the IR camera. As you see, the image is the top red part and the object is the bottom red part, and they're both getting hot. Alright, so we have the same setup this time, except instead of a mirror behind it, we have a lens in front of it. As you can see with the refracting system, we don't get the same conservation because as I move there, the heat goes up, and but then as we bring it back into here, the heat value goes down.
We use the spherometer to find the sag of the lens, and then from that we could determine the focal length of the lens using the following equations. And when the soldering iron's a focal length away from the lens and the lens is a focal length away from the imaging camera, then we know the magnification will be 1 to 1.